The round was good. I'm happy that I already saw a few the round was good comments. I wonder what do Codeforces comments say. He was troll, I agree. I thought that people will complain about hacks. Oh, well, I'm happy about this. People not complaining, I mean. Here's the plan for today. I will discuss easy problems, like up to everything except two last, or maybe the very last one. And Ivan, what's his nickname? I wanted to say best dad. A blood test will join me for like later during the stream to discuss the last problem. That's the plan. Pretests were weak indeed. That was not intended. Did I write problem B? Why do you have this question? I provided an idea for B. All right, as I go through the problems, I will say what's mine, what was my contribution. Nope. What was the... Not that either. Damn it, I forgot how to put this to the right. Oh, here we go. Like this. And we're doing A. First three problems will be fast, of course. Problem A. Count integers such that the sum of digits drops just after this integer. An example that you already knew from the statement was number 9. The sum of digits of 9 is 9. Sum of digits of 10 is 1. There is a drop, so 9 is an interesting number. You need to count those. It's pretty easy to guess that the sum of digits drops if the last digit is 9. So interesting numbers are 9, 19, 29, and so on. So the statement is count numbers with last digit 9 up to n. It's clear that the answer is around n over 10, and you just need to check if you need to do some rounding or anything like that, because once every 10 numbers we get plus 1. If we just do this, then for 9 we would get the answer 0 if you just use this formula, rounding down, and that's bad. If you round up, then this is also bad, because you will get answer 1 for just all the n's from 1 to 9. Either you need to handle that with an if, like if n modulo 9 is 0, then do something, or you need to pretend that n is bigger by 1. N plus 1 divided by 10 is correct. Because then for 9, if 9 is in the input, plus 1, that's 10, divided by 10, that's 1. When the system test starts. I think it's in a few minutes. But you could also do an if, like if n modulo 10 is 9, answer plus plus, after first computing the answer as n over 10. That's correct as well. Moving on. Reverse string. By the way, I don't like problems like A. I told you that I will say what was my contribution. Problem A is perfectly fine. Just I don't like problems that are only math. Initially, the contest didn't contain this problem. So we had 8 problems, digit sum, then penalty, then backspace, and so on. But we got feedback from testers that the first few problems are too difficult, that low-rated people will struggle. So this is why we added B. The idea for B was mine. And you could also solve it in higher constraints. I will maybe very briefly talk about it. That was loud. what do we do in B? In B, you have a string, the first one, and you start somewhere, you move to the right for some time, and then to the left for some time. That's it, in this order. D is too easy for D. I don't think that's what... I mean, it was C before. And tester said that's too hard, so we just added a new problem. Reverse string was added very late, like 2 days ago. Also because of that, B and D are a little bit similar, just because B is added. What's happening here? We have some string, A, B, C, D, E, F. You put a chip somewhere. A chip is like a small coin. I answered those questions a few times. What is a chip? So just imagine some kind of circle, maybe colorful one. Let's say you can put it on C, and then you can move it around. Let's say it's on C, then D, then E, then D. And every time you put it somewhere, you write down the character. So if it started on C, then D, E, D, then this is the whole journey, the whole path. This is the string we obtained. The question is whether we can get another string. Because of low constraints, up to 500, we can do a brute force, or almost brute force, where we aim for n cubic. So the complexity will be n cubic. But what is the brute force? Well, we can iterate over where do we start. So that's one for loop. Let's say we start from this character. Then over how much we move to the right. So we iterate over, let's say, some right bound. You can call it L, call it R. You already have two for loops, over L and over R. And then from here, you will be too slow if you also iterate over where to end. Like, will you move here, or maybe there, and so on. But you know where you should end if you know the length of the second string. If, let's say, the second string is of length 6, and here I already have 4 characters, I know that I need 2 more. In this case, if I covered B, C, D, E, and I want 2 more characters, I need to get back and get D and C. So it's uniquely determined where is this, how long we will go backwards. Let's call this the end. And we will move from L to R, then from R to end. You can iterate over L, iterate over R, and then end you can figure out with math what should be the length. And then that's n squared so far for iterating over LR, and then you need to check some substrings. For example, by using a substring function to get substring from here to there, plus substring from here to there reversed, and compare that with the second string. I will write down the pseudocode for this. For a moment, full screen. For every L, for every R bigger than L, I don't want that. For every R bigger than L, and you can figure out by using math, using length of the target string, and now you check if substring of the first string from L to R plus backwards, so reversed substring from end to R minus 1, whether this is equal to the target. If so, you got the answer. And n squared from 2 for loops, and linear from getting a substring or comparing. So n cubic total. This is the total time complexity. Or what you could also do is, instead of grabbing substrings like this, you could, for every L and for every R, check if that's BCDE is prefix of the second string, prefix of T, and then just keep going to the right, to the left, and check if you have proper characters. Let's say that the target string is BCDE DX. That's the target string. I want to get it here. I iterate over LR, and now ignore this part. So we don't know end. What I do is I check if BCDE is equal to this prefix. Yes, it is. And now, starting from E to the left, so starting from D, I keep checking one by one whether characters match. D equal to D, yes. Then C equal to X, no, that doesn't work. So we stop. But if this was C, then it's all right. We got to the end of this target string, so we say yes. Instead of figuring out with math where is the end, we can just, greedily move from R to the left and try to match the whole suffix of this second string. Be careful, of course, for out-of-bounds errors. You cannot go to index -1. All right. Again, what was the button? Alt Control D. Alt Control D. Okay. D was easier? I don't agree. D was not easy. Problem C. Both problems B and C I suggested the story. In C I initially suggested just a standard string with zeros and ones, and then somebody improved it by introducing question marks. Now we discuss C. Oh, how to do better than... okay, so a few more words about B. You can do DP, I think. I think to solve B in n squared without any string functions is DP, where ij will tell you something like from si to left, no, from si in the second string, and tj to the right in second string, how far you can go, or maybe just whether you can get to ends of both strings. Some boolean DP, I think, should be enough. And then in proper order you should update it. And I think once we need to go kind of from left to right through S, and I mean through T, and then from right to left. Something like that. I'm not 100% sure. Let's move to C. We cannot spend that much time on every problem if we want to discuss all 9 of them. Before I do this, let me check the private chat. Okay, so as I said, we will get bled test later. He will help me discuss hard problems. Z function, I think, could be used to speed things up, but it was not needed. C. Penalties. The statement was quite tricky. I'm not happy about that. Why was E a troll? I don't think it's a troll. It was a nice solution. In C, you need to understand the statement, of course, but it describes real rules of penalties with the suffix being known as well. So if you know what would happen with some question marks, some wildcards, then where this would be stopped. I got the idea while watching Euro, of course, like a week ago or so. For example, if some kicks already happened and now 3 are remaining, you can figure out that teams B, A, B will get those kicks, assuming that first team is A, second is B. So B has 2 more, A has 1 more. If you know the score out of this, maybe let's say A wins with score of 3-1. Then you can figure out if B can tie or win. Or maybe A for sure will win. In this case, B has 2 more kicks, so it's not over yet. B can tie. B can get a draw. Okay, so it's not over yet. You need to move forward. But if this is 0 here, so you move, now you're there, you cover this prefix of size 8, and it's still 3-1 for A, for team A, then it's over, because B will get only 1 more chance. So right now, during a real football match, it would be over and they wouldn't even play anymore. So what's the logic if there are no question marks? If there are no question marks, you need to do something like this. Let's say that the score the current score of team A is just uppercase A, of team B it's uppercase B. What we need to check is something like that, whether A is greater than B plus remaining B. Remaining B says how many times till the end B will have a chance to score. If this is the case, then we know that A wins and it's over. We just need to maintain values A, B. So whenever we get a new digit, if it's 1, we need to check parity of the index to know if we should increase A or B by 1. Here, index I is equal to 0, and whenever index I is even, we increase A by 1 if there is a score, if there is a goal. And remaining B, you can either kind of go backwards to figure it out or use a formula. I think that if this is the current I, then the remaining B until the end will be something like 10 minus I over 2. Or maybe 9 minus I over 2? Maybe 10. To see what exactly is the rounding here and what we should use, I would just analyze the cases. For I equal to 8, this formula will give me 1. That's correct. There is 1 remaining B. For I equal to 9, there is, well, this is 0. That's bad. So I think we should use 11. So for I equal to 9, so everything up to here. Oh, this is not 9. Sorry, I'm stupid. This is I equal to 7, I equal to 8, I equal to 9. So for 8 it's still 1, for 9 it's 0. Everything is okay. So you can use that if you know question marks. Then, one solution to this problem is to try all possible replacements for question marks. If you do that, you'll get the time complexity 2 to 10th power if there are 10 question marks, or let's say 2 to n, where n is equal to 10, multiplied by the number of test cases. So it's O of this. Rating level of this question, I have no idea. I'm not better than you at judging that. As I'm Lord said, you can maintain, no, Noobmaster said that, for this remaining B and remaining A, you can also maintain a variable. That's fine. Okay, so you can do that. Just replace question marks in various ways, check what's the answer in that case, or just figure this out with logic. If we want A to win as early as possible, so we want this to happen early, then whenever there is question mark for A, like here, look at this blue spot. A kicks that, and we want A to win as soon as possible, so let's just replace this question mark with 1. If B has a question mark, let's replace it with 0. So, if we want to minimize the time when A wins, we replace all question marks for A with 1, all question marks for B with 0, and we run the algorithm. Then we start that answer, of course, but then we do the other way around. We want to make B win as soon as possible, so we replace all B's question marks with 1, A's with 0, and we run the algorithm. That's it. Okay, that's C. In D, I think I will skip to E because I didn't care much about D, unless you quickly tell me the solution. Is greedy here okay? What do we do? Some greedy with a stack? 217, stop spamming, it's not related to this to the stream. Start from the back. Go backwards. Go reverse. Okay. So I don't know a solution for D, but I will try to do it. There is a string that describes what characters we used, like A, B, A, B, A. But actually, instead of every character, you could use backspace. And I will simulate this now. I will type AB, but then instead of A, I do backspace. Now let's do BA. This is one string I could obtain. Another example, instead of A, let me click backspace. Click, nothing happened. Then let's type BA, BA. Okay, that's it. And we want to figure out if we can type this with some characters replaced with question marks to obtain that. How do we do it? Apparently, as the chat tells me, we go backwards. Let's see. Then tell me if I'm wrong. If the last character matches this one, then we just leave it and we remove both. And we continue like that. What happens now if the last character doesn't match? Let's say that this is A. We want from this to get BAA. I'm looking now at the chat to see if you tell me that I'm wrong. If I want to obtain A, certainly it shouldn't be thanks to this B. So this B needs to be a backspace. Now this backspace needs to kill one of previous characters. It will kill the previous character A unless this is also a backspace. So maybe this is possible. Or maybe B will kill something earlier and A will kill something earlier. So they will in total kill some two characters. But I claim that it's anyway okay to say that B will kill A. So last character will kill second last character. Why is that? Because if it's optimal, given this first string, to say that B is a delete that kills something and A is a delete that kills something, I can, instead of that, do B kills A and those kill each other, and it's fine. We don't need to consider a case where two last characters kill some two previous characters. It's okay to say this. So going backwards, if the last character doesn't match, then you say that this last character in the first string kills the previous one. So you do pop back twice, like this, and you continue. Is this the same as this one? If so, pop both. Otherwise, pop two characters from the first string. You can kill any number of even characters. Yeah, but you can do it 2 by 2. Please somebody tell me if this is wrong. So again, disclaimer, I didn't prepare this problem, I don't know the solution. E. Yes, this is my solution, but did you get accepted? Permutation shift. This is the troll problem. So this, or at least chat said multiple times that this is a troll problem. Why lower constraints on C? Why higher? I mean, the penalty phase in football is 10 penalties. Okay, E. You start with permutation 1, 2, 3, and so on up to n. Not a permutation, a sequence. You shift it a little bit, and then you do some swaps. The key is that there are only n over 3 swaps, not n over 2. And that's a huge difference. Troll problem because it's very unusual. It's very strange. And the solution is strange. Again, I didn't code this solution, so if I'm saying some bullshit, do tell me. Here's observation. Observation. At least n over 3 characters must match. If I saw this observation, first I would think about randomized approach. It's not needed, but we can do that. What does it mean? That if you look, let's take some input from the sample, 2, 1, 2, 3, 1, 4. What can be the shift? Well, in particular, maybe it's 1, 2, 3, 4. Okay, maybe somebody shifted 1, 2, 3, 4 into this, and then did some swaps. But that's impossible, because you would need at least n over 2 swaps to change this into that. Because there are no matches, you need at least n over 2 swaps, at least. But you know that m is smaller than that. Half n of swaps are needed to change this into what's given, because there is no match. There must be at least one match. What about 1, 2, 3, 4? Well, there is one match, but for the remaining 3 positions, there is a rule that to change in any way k positions, you need at least k over 2 swaps rounded up, because otherwise you will not touch some values, right? And from this we know that some characters must match. Like, this is the exact claim. Now, looking at every value, like looking at 2, I know for what shift it would match. 2 works, like there is a match if we start with 1 being here, then we put 2, 3, 4. So I will say, if 1 starts there, let's do a plus, or I will just put a plus here. Plus means if a shift starts from here, if there is a 1 right here in the blue plus, then I will have a match with that. What about 3? Yet again, if another plus. If 1 is here, then 2, 3, and we have a match. Great. What about this one? If the shift starts here, 1 is exactly here, then 2, 3, 4. And we have a match. And for this 4, if 1 starts here, then we have a match with 4. You count those pluses for every value. Let's say, in general, if you see x here, then using simple math you will figure out where is 1. It's something like, if this is 2, then 1 is here, right? So in general, if this is position I, then you're looking at position I minus x minus 1. Just it wraps around. Maybe you will be there, and you will figure out, oh, here we need 1, so that here it would be x. So for this position, you increase the count by 1, and then you look where you say count of this, c of that, plus plus. And then you see for what shifts the count is at least n over 3. There will be only 3 such places. If n times you increased some count by 1, then only 3 values in that count array can be at least that. Done. Each of them you check in linear time. Are you responsible for this weak test 4b? I think I'm equally responsible as everybody else preparing the contest. Like, we didn't notice it. So I would say in such cases, testers are responsible and organizers, but also, as I mentioned, B was prepared late, so testers weren't that responsible. So yes, you can fail me as much as other organizers. Remember that weak tests, it's more the fault of whoever checked after than whoever created tests. You can always create weak tests, but just later none of us noticed. This clear? We can move on. My internet doesn't work. Okay. Once again, only 3 shifts will have allowed counts of matches. Didn't understand n over 3 parts. I explained that at the very beginning. Otherwise, we would need too many swaps, and this is related to this condition. You will only touch 2m. Let me explain one more way. Let's say that n is 100. M is up to 33, so you will only touch at most 66 numbers with swaps. At most that many numbers you will reorder. So at least 34 numbers must match. Oh, also, regarding later checking the shift, it's quite standard where you treat this as a graph. If you see that 3 should go to position of 4, 4 should go to position of 7, and 7 should go to position of 3, you look at such cycles, and cycle of size k requires that many swaps. Or k divided by 2 rounded up, maybe that's a better way to put it. Cycle of size k requires that many swaps. K minus 1? Uh, 2 requires 1, 3 requires 2. Really? K minus 1? Three requires 2, so I'm correct. But 4 people said K minus 1. 4 requires 3. So maybe K plus 1 over 2. Oh, people just say that K minus 1. Okay, sorry. You're right. You need K minus 1 swaps. You're right. Like in a big cycle, when you swap this, you get cycle smaller by 1, unless you get cycle of size 2. Yeah, this is a well-known fact, so I said that without thinking. Okay, now next problem will be F. Next, F. I'm grabbing bled test. I hear you, but people don't, so I need to click some stuff.
Okay, so I hope there won't be too much noise in the background.
There isn't, and I think people hear you. Chat, please confirm.
Okay, do you hear me?
Chat, say something. Okay, yes. In a moment we'll start talking about F. F and G I know solutions of. H mostly, and I know nothing about. To avoid the delay in screen sharing, I will share you my screen directly, so you don't have any delay. I need a minute here.
Okay, so I think I'll start my screen sharing. Okay. Do people see my screen now?
They don't right now, but I need to click some stuff around in OBS.
Okay. I'm waiting.
I wonder how to do it to get good quality. Full screen. Yeah, that will be tricky. Okay, what I can do for sure is I can go full screen. Okay, that's more complicated than I thought. We will figure out before, I think, H. because starting from H, I will need your screen. Does that sound fine?
Okay, so a few words about the problem F. The main thing you should notice in this problem is that the whole array, the whole array has distinct numbers. There are no repeating numbers in the array. So you have to compute some value. I hope Camille shows it, this value on his screen. So we need to compute this value for all of the prefixes of the array, and we need to somehow use the fact that all of the numbers are distinct. Okay, so the main thing we will use is that we can rewrite this modulo part with the following one. X modulo y is equal to x minus x divided by y, rounded down, and then multiplied by y again. So I hope it is clear.
I will show that with some simple example. Say you have 38, or something like that. 38 modulo 10. One way to look at it, if you don't know how to compute modulo, is to divide. So when you divide, you know that you get 10, you get 3. Right? This is a 3. Multiplied by 10, that's 30. And this is actually a definition of remainder and division, that remainder is whatever is left after you divide. In this case, 3 times 10 is 30, plus the modulo, that's 8, it's 38. Right? 8 is the modulo part. So from this directly comes the thing above. Like what I wrote here exactly is x over y, it's here, x over y times y, that's this, plus 8, that's that, is equal to x. Very well-known formula, and like, you should, in first seconds of solving this problem, consider using this one. All right?
Okay. So the thing we will use is we can group some pairs of numbers according to the value of x divided by y. For example, let's say that y equals 1. Then there are up to 300,000 different values of x divided by 1. So 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, and so on. So what happens if we divide by 2, for example? Then 1 divided by 2 is 0, 2 divided by 2 is 1, 3 divided by 2 is 1. Well, we do rounding down always. 4 divided by 2 is 2, and so on. So, in fact, we will have no more than, I think, 150 thousands of different values when we divide different numbers by 2. So, for dividing by 3, we can get up to 100,000 different values, and so on. So, in fact, if for each y in this division, we somehow group the numbers that give the same result of x divided by y, we will get not a large number of groups. In fact, this can be estimated using the harmonic sums. So I think most of you are familiar that harmonic sum is a sum of something like 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3 plus etc. and up to some number 1 divided by n. And it is close to the logarithm, to the natural logarithm of n if we sum up this number. So in fact, if we try to estimate the number of groups with well, for each possible value, for each possible value of y, we estimate the number of groups. The total number of groups will be something like 300,000 multiplied by the logarithm of 300,000. So the total number of groups, of these groups, is not too large. well, if we can somehow process these groups, then it will be much easier to solve this problem. Okay,
So
so
I agree that the total
now,
number of groups is small, but for now we have no idea what to do with those groups. But also, before that, I will again
yeah,
show people
and
some example with values. The idea is that when you look at, for example, y equal to 10, so when you have in the input number 10 and you consider what is the contribution to the answer from values x modulo 10, then focusing on x divided by 10 is easier, and you say that this value of x divided by 10, like, not everything from 0 to 300,000 is possible. X divided by 10 can be 0, it can be 1, and so on, and it can be up to 30,000. That's 300,000 divided by y. And we are going, for given y, iterate over those. So given y, we will have a for loop over 0, y, 2y, and so on, up to 300,000. And just like primesieve, the time complexity of that in total is m log m, thanks to the fact that the input contains distinct numbers. Right,
okay,
go on.
so what can we do about these numbers? This fact that the number of groups is not very big. Okay, so we will maintain some data structures. I believe that the easiest solution maintains something like 2 Henry trees with a query like add something to the value and get a sum over a segment, or maybe you can replace Henry trees with segment trees because the time limit was generous enough to allow even recursive data structure. Okay, so we'll need some kind of logarithmic data structure like Fenwick or segment tree or something like that. Okay, so what are we going to do? For every, let's start with a prefix of just one number, the first number, and we'll expand it while recalculating the total value we need. Okay, so how do we recalculate the value? When we add a new number, so let's say that our prefix contained k numbers, we want to add the number with the index k plus 1. Okay, so there are two types of connections we have to consider. We have to consider k divided by all numbers on this prefix we have already processed, and we should consider the opposite connection, all values on the prefix divided by this number k. Okay, so let's keep track of the number of all values on the prefix. So for each value on the prefix, we store 1 if we'll store 1 if some value has existed on the prefix, and 0 if some value has not existed on the prefix. Now we'll deal with the connection like the new number divides old numbers. So we'll deal with the
Okay. You want to do the other way around, one y modulo x.
Okay, well,
or not?
Sorry. Okay, so
you want to do earlier modulo later or not?
The new divided by the, well, we'll estimate the sum of the number. Well,
I think you're saying the later modulo earlier. So new modulo everything previously.
Yeah,
Okay.
the later modulo the earlier. We can rephrase it like the later divided by early multiplied by early, and we need to subtract these values. So in fact, let's try to find the segments where we get the different division value, the different division values for the letter divided by format. So for some lower numbers, we will, for example, if letter divided by, we divide the new number by 1, we get the new number exactly. If we get divide the new number by 2, we get the new number by 2 rounded down. So we'll find all of the segments where this value of the new number divided by some old number changes. According to our estimation, this total number won't be large because, well, we had this estimation with the groups. So what to do with these segments where the new number divided by some old number gives the same value? We can query in our family tree or segment tree the number of elements belonging to the segment, or maybe even the sum of elements belonging to the segment. So for example, let's say that our new number is 10, and some old numbers are, for example, 6, 7, and 8. We know that 10 divided by 6 equals 1, 10 divided by 7 equals 1, 10 divided by 8 equals 1. So we can just sum up 6, 7, and 8, and 10 modulo 6 is 4, 10 modulo 7 is 3, 10 modulo 8 is 2, but 10 modulo 6 plus 10 modulo 7 plus 10 modulo 8 is something of the following line.
Okay. I will stop you here again, and we'll talk about example numbers to make sure that people understand what's going on. So we want to, for new y, here y equal to 10, I want to sum up over y modulo x over all previous x's. I already figured out that y modulo x is the same as this strange thing. Of course, it's very easy to sum up over y because, well, I'm looking at y, so I know that 4 times if I add y to the score, in total I have 4 times y, easy part. But what about the second part? Not only the green thing, but the full x times the division. For every x from 6 to 9, yes, for every x in interval from 6 to 9, if there were such values, then we know that the division is equal to 1. So this white thing will just be y divided by x. Y divided by x is 1, so it will be just x. So I need to subtract, remember this is subtraction, I need to subtract here 6, 7, and 8. I need to subtract the sum of values in this range. So if all the previous values we will keep in some data structure, I want to now ask about the sum of values from 6 to 9, and I will say that in my score I have minus this sum of values. All right, go on. Then I guess those with division equal to 2.
The same thing applies to other segments. For example, we know that 10 divided by, for example, 4 equals 2, 10 divided by 5 equals 2. So we have a segment of 4 and 5. So we do the same thing, but instead of just subtracting 4 and 5 from this segment, we subtract 4 and 5 multiplied by 2, because our division result is not 1, as was for the segment from 6 to 9, but our division result is 2 in this segment. So for the number we process this step very in each segment, sum of elements, the sum of elements in this segment, multiply it by the value of the new number divided by some number in the segment, and this is the value we have to subtract from the answer, because remember, this is the value of new number divided by each number multiplied by old number. So this is exactly the value we have to subtract when we take the new number modulo some old number. So I hope this part is clear.
Okay, let's again see some examples. Also answering Gupta's question. We don't, for y, iterate over its possible divisors or anything like that, because what we did is earlier for x, we actually did something in a data structure. We'll see that here. Let's say that now we haven't yet discussed the full solution. We don't see what the code will do. But the second part here, after getting the sum in this range, is that what is going on? The division y divided by x can be 2. So every x in range from 4 to 5, it would be taken with multiplier 2. But we can look at it in some other way. Earlier for 4, because in order to get nice time complexity, for every number I can iterate over its multiples, and then in total it's m log m. So the idea will be, for even before seeing this y, even before seeing 10, when I'm looking at x equal to 4, I will know, hey, later if y is equal to 10, x will be taken with multiplier 2. It's this white part here below. Right? So x equal to 4 will do the following. Like without knowing 10, without knowing anything in the future, it will say, if there is some future y from 8 to 11, then it will take me with multiplier 2. So given a partially known sequence, looking here at 4, and not knowing future values, for this x equal to 4, you know, if later there will be some y in range from 8 to 11, then I know that the division is equal to 2. So I need to say, for all y's in this range, they will get in the answer this, so minus division times x. I'm x equal to 4 right now, x equal to 4. So for all those, I need to say minus 8 to the answer. I do minus 8 in range from 8 to 11. Similarly, I do, like if y is, maybe with a different color, if y is in range from 12 to 15, I will do minus 12. Because I know that y, when it's in brute force, when y looks at this previous x, like y is somewhere later, x is here. When y looks at x, it will take y divided by x, rounded down, that's 3, multiplied by x. So this value, x multiplied by division, is equal to minus 12. Y will want to add minus 12 to its answer. So the current x equal to 4, in range from 12 to 15, it should add minus 12. And later y will ask the same data structure about just the value at point. So x equal to 4 triggers minus 4 in range 4, 7, or 4, 8 exclusive, minus 8 in range 12 to 16. Ivan, you can correct me if I'm wrong. You should see my screen in like Twitch. Oh, minus 8 in range 8, 12. Minus 12 in range.
I can't see your screen.
You can't?
Okay, sorry. Just a minute.
So I want to you just. Okay, I want you to confirm if I'm not saying some bullshit.
Now I see it.
Yeah. So when you look at x equal to 4 somewhere, you're cutting out. Please repeat.
Yeah, these are the operations we have to perform. So, in fact, this data structure, it's kind of obvious now that this data structure can be something like a segment tree with an addition on segment, or where the addition on segment and the value in point. So this data structure will store the value we will need to subtract from the answer when we add some number I to our print. So the value in the point is equal to value, we need to subtract from the answer when we add I to our script.
Yep. And this is how we now we have logarithm from segment tree and logarithm from iterating over multiples. So the time complexity becomes log squared. It's what, m log m coming from iterating over multiples times another log from using a segment tree. This logarithm, I guess we can also say it's of size m. If it's in segment tree built on values from 1 to m, that's quite convenient. So I would say m log squared m. If n is very small, maybe we should here use another logarithm, or doesn't matter here. Let's just assume that n is equal to m.
And okay, so we have discussed how to process these new values when the new number gets divided by some old number. But we need to process the other way around as well. So we need to do something about the old numbers dividing the new number. In fact, it's a bit easy.
I'm not hearing
What
you
shall
well.
we do? Okay, so can you hear?
Yes, now I can.
Okay, so we need to process this the other way around. So the old numbers divided by the new number. Okay, so we know that for the new number, we can find these groups when the old number divided by this new number equals some value. For example, if the new number is 8, we know that all numbers from 1 to 7 get 0 as a result of the division. All numbers from 8 to 15 get 1 as a result of division, and so on. So we can just keep track of the number of elements in each set, and for each element in some segment, we subtract the new number supplied by the result of the division from the answer.
Okay. I think we will not go into details again here because it's very similar part. Also, I believe that the written editorial explains in more detail this second part that we kind of skipped here. But yeah, the other direction, so x modulo y, where y is later, y is more to the right, in that part, what interests us at all very much is this division. So for y, you need to iterate over its multiples. And there will be some ranges of x with the same multiplier. So this time y will ask about ranges. Editorial, I don't know if it's published. Do you know if editorial is published?
We'll publish it somewhere in something like 2 or 3 hours after the contest.
Okay. The editorial for almost all problems is editorials for almost everything are ready, I think. So maybe we can do the not full editorial a bit faster. Well, anyway, this will be more detailed in the full editorial. If you viewers, if you understand the first part, you should be able to figure out the second as well. 1 minute summary is that when looking at y, you want to know what's the sum over y modulo everything previous to that. You write down using this special formula. Instead of modulo, you want to use division, and you want to in some way iterate over possible values of division. And for every x, so every previous value, if you iterate over its multiples, you will get some kind of ranges. And in every range, for example, we said for x equal to 10, what was that? No, it's here. For x equal to 4, if y is in range from 8 to 11, then it wants to get minus 8 to its answer. So x equal to 4 triggers minus 8 to range of a segment tree. Okay. Now FG. For starting from H, I think you should share your own screen, Ivan. But F I can just, G I can just draw. Is that fine? I don't hear you if you're saying something. I still don't hear you.
Okay, can you hear me now?
Yes, now I can.
Okay, so I hope I can share you. I hope I can share you my screen when explaining the last two problems.
Yeah, sure. I thought that this is the plan. I thought that I was going to explain F and G, and then you would explain HI. But now I will talk about G, the common divisor graph. This problem was modified. The initial idea for the problem was different, and the solution was more complicated. We made some changes. You can all notice that this condition with AI plus 1, it doesn't look very natural. Initially, we just said that you can increment value by 1, but this makes everything more complicated. So somebody came up with this trick of saying, oh, actually, we create multiplication of AI and AI plus 1, and it's a little bit like allowing AI to be also increased by 1. It was cheating a little bit by the organizers. Okay. The statement is that we want to move between nodes and you can, or values, and you can move between two values directly if they have a common divisor. In order to make it possible to reach from one node to another, or from one value to another, you can create new nodes. The statement said that if there is some x in the sequence, you can create x times x plus 1. But you should understand it, in fact, and it will be much easier if you just assume that x replicates and creates x plus 1 next to it. Let me show an example. Let's say that you have value 5. There is also 25, so they are connected. There is also maybe, let's say, 27. 27 is not connected to everything else. But 5, yes, you can create 30 thanks to that. And the statement actually says that there is 30 and then stuff is connected. Cool. But what's easier to think about is that 5 creates 6 and they are connected to each other. Together they create 30. It's the same thing. And now 6 is just connected to some new stuff. In this case, 27. So instead of creating 30, you just create 6. Okay. At the very beginning, you can every number connect to all its prime divisors. Like 27 is just 3. For every number, we care about its distinct prime divisors. Or for 100, the prime divisors are 2 and 5. It doesn't matter that it's divisible by 20, for example. It's as well, this could be 10. So what we do with the input is every such value connect to prime divisors. You can assume that those nodes exist. If in the input you were given additionally 5, and you created edges, all the edges, without creating new nodes, everything would be connected in the same way. So let's say it's like that. 27, that's 3. 6 is connected to 3 and 2. You have this kind of graph, and thanks to that you have connected components. You do something, you do prime sieve, sure, and at the end you will get connected components. For example, if the input is 10, 2, and 3, the connected components should look like this. Maybe this first one will also have a 5, the prime 5. That doesn't matter much if you explicitly have that prime or not. You have connected components. If two nodes are in the same connected component, the answer is 0 to move between them, because you can just do it. Now, for every node, we consider increasing it by 1. For example, 3 can be increased up to 4, and we look then at prime divisors of 4, that's 2. So we connect it to a connected component with 2. We know that with cost of 1, with one operation, we can make those two connected components connected. In general, when you have some big connected components, a lot of them maybe, but you see here value, let's say, I don't know, 17, maybe with some others, such that you can travel between them initially without new nodes. You consider for every value 17 can be increased to 18. So if you look for a connected component with 2 and with 3, because those are prime divisors, maybe 2 is here, 3 is here, and you draw the edges. Let's say the edges of cost 1. But that's not everything. Right now with this graph, with every green edge, it has cost 1. It seems that to get from 3 to 2, you need cost 2. But that's not true. Actually, increasing 17 up to 18 allows you to travel between 2 and 3 for free. So not only you connected component with 17 to everything being divisors, prime divisors of 18, but also you connect them with each other, with edges of cost 1. This edge between 2 and 3 means exactly the following. It is possible to increase something else by 1, that's 17. You can increase it up to 18, and thanks to that, 2 and 3 become connected. Okay. So the logic is for every AI, you look at prime divisors of AI plus 1, and you draw edges between all the pairs of prime divisors. In particular, if you see a value like, let's say, 29, then this plus 1, that's 30, and the prime divisors of 30 are 2, 3, and 5. It means adding a lot of edges, green edges, of cost 1. You put edges from 29 to 3, from 29 to 2, from 29 to 5, but also 2, 3, 2, 5, 3, 5. If in total, including 29, there are here k values, k minus 1 prime divisors, and also this value itself, AI, then you will add k choose 2 edges. K choose 2 edges, green edges. That many. Then, to know if the answer is 1, you just, when answering a query, you need to check if there is a green edge between the two nodes. And also the answer cannot exceed 2, because you can make both nodes from a query even. If you have query between 3 and 11, you can spend one operation to increase 3 up to 4, 11 up to 12, and now they are connected. I should have started this explanation by saying answer doesn't exceed 2. So we only need to check if it's 0 or 1. 0 you check thanks to connected components built on the initial graph. Now the connected components each you imagine as being one node, and you draw the green edges between connected components. And then it's not that you run connected components again. It's not that you say that this is one big connected component. That's not true. Every single green edge means it's possible to increase something so that those two would be connected with cost 1. But consider this example. Maybe there is 26 here, and you see that increasing this, that's not a good example because there's a 2 here. I need something else. Let's just assume that 2 isn't here. Say there is 26 here. If I increase this by 1, I have 27. And then I'm neighbors with 3. So draw an edge like that, an edge with cost 1. But this doesn't mean that 26 is connected to 17, because those two green edges, they are about something else. This green edge means that I can move like that if I increase this guy by 1. This green edge says I can move like that if I increase 17 by 1. And that's it. It's not that I can travel between those. I can, but with cost of 2. Well, there is also, actually, if we increase 17 up to 18, then it creates this edge anyway. So This is a stupid example because generally even numbers are here. They allow us to do a lot. The very summary of everything. Answer doesn't exceed 2. Then, step 1, find connected components. Maybe step 1 should be run primesif to find distinct prime divisors for every number. Step 2, find connected components of the initial graph. Step 3, draw green edges between connected components. Each of them is created by looking at prime divisors of AI plus 1 and drawing the green edges between all the pairs, like I explained here above. That's it. Chat, any questions? The time complexity, if to draw green edges if you use a set, it seems to be around, let's say, n times log squared times log. This log comes from a set. This log squared comes from iterating over pairs of prime divisors. For example, 30 has 3 prime divisors. Some maybe 1000, so 1000 has 2 prime divisors. Number up to n, or up to 1 million, can have up to like 7 prime divisors, I think. So this is not really log. I think it's called log star or something like that. On average, it doesn't exceed this. So let's just say that this is the time complexity. In this case, not many numbers have so many prime divisors. And you can easily check the worst case by checking all numbers up to 1 million and finding the worst out of them, and assuming that those are AI plus 1. And then the very worst thing we can have in this problem, I checked when preparing tests, is that this value, so how many times we can try to put a green edge, 1,700,000. This is more or less the sum over number of distinct primes choose 2 over 150,000 worst numbers from 1 to million. And that's it. So even in this case, 100, so the very worst case for us is that 1,700,000 times we put a pair to a set. Okay, Ivan, you there?
Okay, I'm here. Can you hear me?
Yes, I can. And I'm going to show you on the screen.
Okay, so tell me when everyone can see my screen.
Now everybody can see your screen.
Okay, so I will discuss problem H in detail, and I'll say a few words about problem I, because, well, discussing the solution of I in full detail may take something like an hour or 2. Okay, so the problem H had a pretty simple statement. You are given an array and some integer called k. Every element in the array is not exceeding 2 to the power of k minus 1, and all elements were distinct. Let's define the XOR distance for some number x, not necessarily present in our array, as this formula. So we XOR every element in our array with x, and then we find 2 closest to each other, and then we take the distance between them. So for every integer from 0 to 2 to the power of k minus 1, we have to calculate this value of distance. And the constraints were something like k up to 19. The array could have something like up to 2 to the power of k elements. And, well, usually when you have to, when you have some constraint like something is up to 20 or to 19 or something like that, it means you are dealing with bitmask dynamic programming, we won't deal with bitmask dynamic programming in this problem, but we will deal with some other structure that can help us represent the bitmasks. And this structure is called a trie. Okay, so a trie is a structure that is usually storing some strings, but we will interpret each number as a binary string of length exactly k. So for example, let's say that we have a number 3. In its binary representation, it's something like 0, 1, 1 in binary. So if we store this number as a string in a trie, it should go here, 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 and here. So it should go into this node. Some other number, say 6, is equal to 110 in binary representation. So it should go, I think, here. Okay, so I will create a trie for every number, even if it is not present in the original array, but I will store whether some number is present or not. Okay, so there are two main solutions that utilize tries in this problem. Both of them use the following trie structure. I think I'll move to the code to explain a trie structure better. So, okay, a node in a trie always has some left node or left child or right child if it's not a leaf. So it's usual for binary trees, and binary
Just
trie is a
remember that we're talking about second last problem. If somebody doesn't know try, then let's assume they cannot solve this problem, I think.
Okay, but I have some modifications to this try.
I see. Okay.
To calculate the answer easily, I will store 4 additional values in each vertex of the trie. Okay, so we will store the maximum value of the in the subtree, the minimum value in the subtree that is present in our original array, the answer for this subtree, and the length of this subtree. Okay, so the length is, well, the number of nodes, the number of leaf nodes in a subtree. So for example, for this node, the length will be equal to 4. So each node will represent some segment of values, and the length in the value len in my code is just the length of this segment. Okay, so what about answer? The value of answer will be used to find the minimum distance between two numbers in the same subtree. So ans is the minimum distance between two existing numbers in the subtree of this node. Okay, so I made a few functions that allow me to create a leaf for the trie, allow me to create a vertex that has some left and right child. And well, the calculations are a bit easy. Well, the length of the subtree is just the sum of the lengths of the left and right childs. The maximum value is either in the left subtree or in the right subtree, but I store these maximum and minimum values relative to the start of the segment. So for example, let's say that we have this number 6, and we store it as the maximum number in this vertex. We store it not as 6, but we store it as 0, because this vertex represents the segment 6, 7, and the relative position of 6 in this segment is 0. For example, in this subtree, in the subtree of this node, it represents the values 2 and 3. So this number 3 will be actually stored as 1 in these minimum maximum values. Okay, so That's why when I recalculate this maximum and minimum values, I add the length of the left subtree to the minimum and maximum values in the right subtree. And well, if some subtree is empty, if it doesn't contain any values in the original array, well, I just store infinity or minus infinity. Okay, so the answer can be recalculated in the same way. We just take the answer from the left subtree, take the answer from the right subtree, and try to take the rightmost number in the left subtree and the leftmost number in the right subtree. They are conveniently stored in these values min_val and max_val for the right and the left subtree respectively. Okay, so now we have some data structure that allows us to maintain this trie with the answer on it. Okay, so first step of our solution is to build this data structure on the original array. And this will be the data structure that answers the problem for x equal to 0. So if x is equal to 0, then nothing changes, and well, nothing changes in the structure of this trie. So initially, the structure just stores the answer for 0. Okay, so what happens if we try to change some bit of this number x? For example, we initially had a structure. We initially had a structure for x equal to 0. Let's say that we change the second bit in x, so it becomes not 0 but 4. What happens? In fact, all we need to do is take this subtree. I'll move it here. Take this subtree. I'll move it here. I think I've taken something more than I needed. And swap them. So we put the left subtree in the position of the right subtree, and the right subtree in the position of the left subtree. Okay, so I hope that my drawing is clear enough. Okay, so when we do this, we need to recalculate the values for the root node. Okay, so we know how to flip one bit in our x. But what happens if we flip some other bit? For example, let's say that we flip the lowest bit, the bit responsible for the the lowest significant bit. So let's say we advance from x equal to 4 to x equal to 5. It means that we have to swap these leaf nodes. So we swap these two nodes, we swap these two nodes, these two, and it means that we have to rebuild the whole structure. And obviously, we don't want to do a lot of rebuilding the whole structure because, well, this structure is built in something like O of n. Because flipping some bit may result in different time to rebuild the structure, we will have to find some way to rebuild this structure efficiently. So we don't swap low bits often, but we can swap high bits often because rebuilding a structure when a high bit is flipped is much easier than rebuilding a structure when a low bit is flipped. And the order we will do for this is called gray code. Okay, so what is gray code? Suppose you want to iterate through all numbers from 0 to 2 to the power k minus 1 by swapping 1 bit in each operation. What we will do? Okay, so let's say that we want to iterate through the numbers having 2 bits. Okay, so how does gray code work? First of all, we shall iterate through the numbers having the highest bit equal to 0 in some order, and then through the numbers having the highest bit equal to 1 in some order. Oh, okay. No. For our problem, it will be the other way around. We will group the numbers according to their lowest bits. So we iterate through these numbers in some order, and then we iterate through these numbers in some order. So we will iterate through these numbers recursively. In fact, I think I'll rather show you the code for this breakcode pattern. Okay, so let's say that our recursive function will give us the gray code, and x is the bit we are currently grouping by. So all numbers we have encountered so far are grouped by the bit on position x. Okay, so what shall we do? We will if it is the last bit, we'll just write the answer for the current number from our data structure. If it is not the last bit, we will try to move on to the next bit by calling this recursive function through with the argument x minus 1. So we will group the numbers by the next bit. Okay, so here I have a function called swap segments that rebuilds our data structure when some bit is swapped. So this function swap segments, how does it work? It just swaps the neighboring nodes on some depth level d. So for example, when we swap the highest bit, as I've shown in my drawing, when we swap the highest significant bit, we need to swap the children of the root, so the nodes on the first depth level. When we swap the second highest bit, we swap the nodes on the second depth level, and so on. And when we flip a bit in this gray code, so we flip bit x, we swap the nodes in our data structure on some depth that is somehow corresponding to x. Okay, so after we flipped this bit, we do the same as we were doing before flipping this bit. So we either write the result for the current value, or we call the function recursively, grouping the numbers by the next bit. Okay, so how often will we swap a lot of nodes? Okay, so in gray code, the lowest bit will be swapped one time. So okay, so bit 0 swapped one time, and this leads to rebuilding the whole structure. Bit 1 will be swapped 2 times, and it leads to rebuilding of the whole structure, but the lowest level. So in fact, we rebuild the half of our structure. So we rebuilt the half of structure. So here we rebuild the whole structure. Here we rebuild the half of structure. For bit 2, we flip it 4 times. So we will rebuild just the whole structure, but the 2 lowest layers. The lowest layer has the half of the nodes. The second lowest layer has 1/4 of the nodes in the whole data structure. So we will rebuild 1/4 of the data structure. So you can see where this goes. We sum up something like S plus 1 divided by 2S multiplied by 2 plus 1 divided by 4S multiplied by 4, and so on. And that's for all of the bits of our numbers. So in fact, we will get something like the size of the structure multiplied by the logarithm of the size of the structure. So we'll get something like 2 to the power of k multiplied by k using the constraints from the original problem. Okay, so this solution uses gray codes to rebuild the structure, but there is an even more efficient solution, which I'll showcase next. Okay, so instead of rebuilding the structure, we will store in each node of the trie not one vector of these values, maximum value, minimum value, answer, and the length, but several of these values. For example, let's say that I'll draw a picture of some node of the trie again. So let's say that we have this little node with 2 children. We have element 0 and element 1. Okay, so what happens if we flip this node by x equal to 1? So what happens if we flip the lowest significant bit? It means that the maximum value will change, the minimum value will change, the answer, and the answer also might change. But what happens if we flip this node not using x equal to 1, but using something like x equal to 2 to the power of 10 plus 1, which is 125, if I'm not mistaken. So what happens if we XOR all the numbers by this value and try to rebuild this node? In fact, nothing changes because we have built our structure so that our values of maximum value, minimum value in our segment are relative according to the segment that this structure maintains. So XORing all numbers in this structure by 1 is the same as XORing all numbers in this structure by 2 to the power of 10 plus 1, and by something like 2 to the power of 5 plus 2 to the power of 3 plus 1, and many other numbers. So in fact, in this node, we store 2 states of this node. One state when this node is sorted by 0. All numbers in this subtree get XORed by 0. And another state when this node is XORed by 1. Okay, so what happens if we have some bigger node? So, for example, it has a subtree of depth 2, not depth 1. What happens? In fact, we can just ignore all values larger than 3. We can build the state of this node for x equal to 0, for x equal to 1, for x equal to 2, for x equal to 3, and do this and assume that for x equal to 4, for example, the result is the same as for x equal to 0. We don't need to rebuild this structure for x equal to 4 because we already have a version for x equal to 0. And the only thing we need is to somehow merge these two structures into one. So, well, when we create a node and we have all the states for its children, we need to somehow learn how to merge these states into the states of the new node. I think it's better to showcase it in my code. So, okay, so when we build a structure recursively for the left child and the right child, the middle value and the left value, well, they are used as in the segment tree code. So the left value is the left L, the left value is the border of our segment, M is the middle of our segment. So we know that each node has the number of states equal to the length of the segment it controls. So for this new node that goes from L to R, we need R minus L different states. How we build them? When we need a state equal to I, we just merge the states with the number I from our children. When we need a state equal to some other number that is not present in the states of our children, it means that this number has the form of I plus the length of the segment for one of our children. So we just do the same as merging them with state equal to I, but instead of the order from left to right, we merge them backwards. We assume that the right child is actually the left one and the left one is actually the right one. So for this solution, we use the same data structure, but we build all its states we need. So for each subtree of our data structure, we build the states. What happens if we XOR all elements in this subtree with some number x? For all numbers x, we are interested in. And of course, for the elements in the lowest layer of our data structure, we need only one state. For the second lowest layer, we need two states for each node. For the third lowest layer, we need 4 states. And I think you know where all of this is going. We have the size of the structure, something like s multiplied by the logarithm of s, which yields the same complexity of to the power of k multiplied by k. So these are two solutions we came up with when preparing this problem. There is a third solution that uses some different observations, but I'm afraid I can't discuss it right now. Okay, so let me check the screen and see whether are there any questions?
People mainly ask questions about test case 19 in D.
What happened?
Everything is all right.
Okay, I'll look into test case 19 later. Yeah. Okay, so shall we proceed to the problem I?
Yep. Do you want to show what? The outline of the solution? This is just the idea?
The main idea of problem I. Okay, so I assume that everyone who's interested in problem I have read the statement. Okay, so first of all, we need to check that this stair array actually represents some permutation, well, that's quite easy. We know that each stair is either ascending or descending, and it means that an ascending stair and a descending stair cannot merge with each other. So if we have two adjacent ascending and descending stairs, well, they can't merge with each other. If we have two adjacent ascending stairs, they can merge with each other only if the values are, for example, let's say that these two numbers 1 and 2 are a stair, which is ascending, and this number 3 is also an ascending stair. Well, these three are merged into one stair. We can rebuild the stairs and their sizes given the stair array with the following greedy algorithm. So let's say the first value in our stair array is 1. It represents a stair of size 1. Then the next value is 3. We pick next 3 values into a stair of size 3. Then we pick the next 3 values into a stair of size 3. And we go on until we reach the end of the array. And if something bad happens, for example, for some stair, the stair values are different, or we reached the end of the array without constructing the last stair, well, the answer is 0. Okay, so we've constructed the stairs and the lengths. What to do with them now? We can write a quadratic solution with inclusion-exclusion. So we need the stairs not to merge. We need to assign each stair some number and direction, the number where this stair starts and the direction where it goes, so that these two stairs don't merge. So an ascending and descending stair can't merge, and if there is a stair of size 1 near a stair of greater size which has its status, then they can merge into a stair with the same status. We can use inclusion-exclusion to calculate the number of, well, we have some constraints. The first stair should not merge with the second stair. The second stair should not merge with the third stair. The third stair should not merge with the fourth stair, and so on. So we can use inclusion-exclusion to write the following dynamic programming. Let dp of n and I be something like we picked the n first stairs and we violated I first constraints on these stairs. So I pairs of adjacent stairs have merged, but they shouldn't merge. So we need actually a third state in our dynamic programming that represents the status of the last stair, whether it's ascending, descending, or whether it's it has size 1. But well, this is the quadratic solution, and in fact, it can be improved with some sheer insanity, I would say, with the following observation. We can represent the values of some dynamic. We can represent the values of this dynamic programming as a polynomial. So in fact, dpik, instead of representing it just as an array, dp of I will be a polynomial of dpik times x to the power dpi0 times x to the power of 0, dpi1 times x to the power of 1, and so on. And in fact, these polynomials can be merged together with the help of divide and conquer and fast Fourier transformation or some other fast polynomial multiplication algorithm. This is the apply of the solution. I will describe the exact solution in more detail in the official editorial, but unfortunately, if I try to describe it right now, we'll need something like 1 or 2 hours to do it. Okay, so I hope you liked the contest. I hope that the issue with system testing didn't affect you too much. Unfortunately, I wasn't able to ensure that pretesting some 2 problems were strong. The issue with the problem B, you can say, is that, the number of pretests on Codeforces, especially on easier problems, is limited. So problem B contained only like 4 or 5, I think it's 4 pretests. So I've needed to construct some cases that would fit into these 4 pretests. So and the problem was with the solution that has a complexity of n to the power of 4. You can actually choose different orderings where you start the loop, where you end the loop, in which loops are started first, which loops are started next. So I tried to break some of these strategies of starting managing these 4 nested loops, but unfortunately I couldn't quite break all of them in 4 tests. So I hope we'll I hope we'll be able to improve this in our next rounds. Okay, so thank you for watching. I hope my explanations weren't too complicated, and we'll release an official editorial in like 2 or 3 hours or so.
Thanks for explaining the 2 hardest problems. I think that always after the contest, the biggest general complaints on Codeforces are about pretests, and indeed we didn't manage to get pretests right this time. But in Codeforces there is this limit of the number of pretests as well, otherwise the queue becomes huge. So it's like a trade-off between fast judging time and the safety of pretests, or the strength of pretests rather. It's easier if there is a contest for 1,000 people, of course. So I'm stopping showing your screen, and I think the explanation is over. Chat, any questions, thoughts about the whole round? I saw complaints on Codeforces that the round was very easy for strong people, and indeed it's true. If there are 9 problems, and I think, yeah, the last 2 are hard, they are interesting. I strongly argue that the last 2 are valuable problems. I didn't invent them, I didn't prepare them, but they are 2 good problems. Everything before that, you can argue, is too easy. I wonder if Division 1 participants would have better feeling if only given the last 5 problems. So if you were given stuff from Permutation Shift as the first one, then Pairwise Modulo and Common Divisor Graph, where Common Divisor Graph is easy but implementation heavy, I think that would be a nice Division 1 round. I don't have a feeling that that's too easy. Or maybe it is. For example, as a coordinator, I would agree for such Division 1. But with combined rounds, you have that feeling that you went through a lot of easy problems when you just code for loops. the IFFT standard implementation? I guess so, yeah. You can use entity, so it's not really FFT, or you can use very precise FFT as well. Not to see Limac in the round. When I create rounds with others, I rarely use Limac because I don't want to spoil which problem is mine. If the whole round is mine, then sure, I can use Limac. H was cute. I agree. H maybe it's not the most difficult, but I think it's best quality of a problem. Short statement and a neat solution, where I might be too difficult and annoying. Right, this is it. The written editorials should already be there. Are they? Maybe not. I didn't see that, but expect them any hour now. There should be some automatized system that publishes editorials just after the contest, maybe for every problem. Because in Polygon, most problems, when the contest ended, most problems, they had tutorial written down in Polygon. I don't know how that works. Thank you everybody for watching. To resolve last one. Oh yeah, last thing for today, I can take a look at the standings. It's sad that BND affected the standings even in the top. I wouldn't want that. That wasn't the plan, to make pretest weak in BND. That was just our mistake. The first full solve was BenQ in hour and 30 minutes. That's obviously very fast. And +9, +14 here. This is bad. You don't want to see this because like, this is bigger than just the full problem D. What else is here? So I wouldn't want to see all of that. Looking at the last 5 problems though, if the top person solves it in hour and a half, well, hour 15 minutes, that's fast. But for a 2-hour contest it would be fine. Around fewer than 10 people would get the full score. Yeah, I think that would be fine. I still prefer Division 1 rounds plus Division 2, not combined. I think it's better with 5 problems. What do you think? Maybe I will ask that in comments in Codeforces. Did you expect people to finish contests so fast? Not in hour and a half, but in 2 hours, sure, it's possible to do 2 hours. Perfectly, the perfect setting is that nobody has time to finish everything, but every problem is solved. There is this metric very well known. I would argue that it's fine if few people solve it in full time, not half of the time, and BenQ was close to that. And another thing is that problem like G, it was mainly implementation. I don't know. Testers didn't find it that easy, I think, but G is an easy problem, easier than this slot. E and F are, I think, what's F? This wing. I don't know, they are fine. This is for sure not bad for Division 1 A and B. I said that at the beginning of this stream. We had 8 problems like 2 days ago. A, C, D. We didn't have reverse string, but testers said this is too hard for beginners. We had digit sum, penalties. Penalties is too hard for the second slot, and backspace. And they said it's too hard for beginners. I agree. After adding B, we also thought about removing one of those, and I think it would be a good idea. Maybe I don't know. I prepared G, so I should like it most. Like, you don't want to see something that you prepared to be removed. I didn't come up with the idea. I prepared tests and the statement. But I think that G was very bad problem, so maybe I would remove this one. But then there is a huge gap from F to H. If you look at the number of accepted submissions and you forget about those fails in B, then ignore the red stuff on the side. So if this is higher, and it should be, then I think that this is perfect difficulty drop. If you look at the ratio of solved, this divided by that, it's almost always 2 or 3. Like, this is perfect. The rating distribution seems to be perfect here. I mean the difficulty distribution. Just maybe too annoying to code. I would remove G, but then there would be difficulty gap. C seemed too easy. Penalties. You know, a moment ago it was the second slot. So we kind of spread the easy problems. Imagine that those 4 problems are first 3, and then we just spread them out by adding 1 easy problem. Red stuff, possible cheaters? No, it's not that. It's about whether a test is in pre-tests or in full system tests, something like that. Okay, like G. I spent most time in G, and maybe because of how much time I spent, I think that it's too easy to come up with a solution, too difficult to code. Hard to say. But it's not that all organizers thought like that, so we didn't remove the problem. And you're allowed to like it. It's not that you're wrong here. If there was one change you could do in this round, what would it be? So I don't like G, maybe I would remove it. And I would obviously fix pretests for B or D. I don't know which one was a bigger problem. Looking at standings, D, right? Yeah, I would fix pretests for D, because that affects the leaderboard a lot. Is it reasonable to remove D? Maybe even that. Maybe even we should remove D whatsoever, but then the gap is huge. A good question though. It's interesting to ask organizers after the contest what they would change. The maximum answer is 2. Oh, that part is cute. Just, you know, the answer is at most 2 is very easy observation for such a problem. This is a very late problem. Division 1 with last 5 problems is fine. With G or without? What's your order? E, F, H, X? What do you mean by X? Is it a typo? X is next to C? No. Oh, something new as D. You mean that it's good to replace? H is difficult, isn't it? I know that you got H very fast, but on average H should be difficult, isn't it? I'm now looking how much time people took. Here I see times around half an hour. I don't know if that's better for C or D. Yeah, so this annoying for division 1, I agree. Editorial is already out. H is something between CD. I agree. I can agree with that this half an hour to, if it takes half an hour to high red, then it's like C+. With 5 problems in a round, I wouldn't know where to put it. The editorial. Somebody said the editorial is out. I don't see it. Roommate is Russian. Sorry to know she's homeless. Very nice. Thank you, Germany. Okay, that's it for today. Hope you enjoyed the round. Sorry about the weak pretests. This is our organizer's fault. Well, if we make another round, we will try to be more careful with pretests, especially of easy problems maybe. But in hard problems, it's easier. In hard problems, you can have a lot of pretests and you just put almost everything in pretest most of the time to say everything should fail pretests if it's wrong. Perfect 3000. That's not on purpose, but thank you. Good luck in upsolving. Editorial should be out soon because it's mostly ready, other than the last 2 problems. Bye.